Okay, got it going?
Yeah.
Okay. So this is the lab that y'all are going to use tomorrow with these spring labs. So you press that in, and then if you hit it, it comes flying out. So this is a situation where you store potential energy, but Mother Nature doesn't like potential energy. Mother Nature prefers kinetic energy. So I've got these two carts, okay, and the masses are the same. And this is what we just talked about up there. Oh, okay. Initially, there's no momentum in the system. I do this, boom. They're both going to move off in opposite directions. So the only way that can happen is if there's no momentum to begin with. To conserve momentum, if their masses are the same, they have to move in opposite directions with the same speed. But if I put a 1 kilogram mass on one of them, I'm going to release the spring again. What's going to happen?
That one is slower.
This one needs to be faster or slower?
Slower.
Why?
Because it's got weight.
More mass.
It's got mass.
More mass. There's no weight, it's mass. After I hit this, are they both going to have the same momentum?
No. See, yes.
Yes, because momentum has to be conserved.
Yep.
So if you define this direction as being positive, this one's going to have a,
Negative.
so the momentums will be the same. Okay? But their velocities won't. So this has more mass, so it has to move with a slower value. So I do this, okay? There is a noticeable difference in those two velocities because of the fact that this has so much more mass, it had to be moving slower to have the same momentum as this one did. So that's if they're at rest. Now you can also have a situation where one is at rest and the other one moves in. Now, in this situation, this one hits and it stops. So if this has like 5 Newton seconds of momentum and it stops, how much momentum does that one have?
5
Five
seconds.
seconds.
5. Okay, cool. Now, if they're the same mass, this one stops, this one just keeps going. Now, I could also have a situation where this one's much more massive and moving. So if this situation it hits, now, this one doesn't stop. It keeps going. But after the collision, is it going to speed up or slow down?
Slow down.
So this is going to lose some momentum. Okay? This one's going to lose some momentum. Where does that momentum have to go?
The other card.
To the other card. So whatever momentum is lost by this one is gained by this one. Okay? Now, I could also have a situation where I'm going to put a more massive one on this one, or more massive by a lot. Okay? So this one's going to hit. Now,
Oh, so you go there.
this one goes backwards. So anytime something changes direction, that's a big change in momentum. Because if you look at change in momentum, mass times V minus V naught, if it just stops, you're just taking it from some velocity to 0. But if it hits and bounces back, that's a much bigger change in momentum because you have to go from a big mass that's moving, some positive velocity, you've got to take it to 0, and then you've got to take it from that value to a negative value. So anytime something bounces, that's a bigger change in momentum than if it just stops, because you have to bring it to a stop and then speed it back up in the opposite direction. So anytime things bounce, that's a big change in momentum. Okay. Now, you could also have a situation like this. Flip this around. So this one's at rest, and this is going to come in, it's going to hit, and then they move off together. Okay, so this is what I refer to as like a California problem, because that's kind of a California hippie thing to do. It's like, oh, let's move in together. Okay, so now you have a combined mass because they moved in together. So this one's at rest. This is going to hit, boom, they're going to move off together. What happens to the velocity after they move off together?
Decreases.
It looks like it decreases.
It decreases. Why? More mass, but it has the same.
Momentum.
Now, here's going to be important algebraically later on. When they move off together, do they have the same velocity?
No.
Yes.
Oh, yes.
Yes.
They all have to.
They have the same velocity. They're moving together.
Because they.
Oh,
Okay.
the two cards. I thought
So,
you meant. Oh.
this one was at rest, this one was moving. After the collision, they both move at the same speed.
Oh,
Yeah.
they both.
I thought you meant before and
I thought you
after.
meant-
No. After the collision,
Yeah.
these two have the same
It's from
speed.
point one card.
Yeah, because now it's just one big massive object,
Yeah.
okay? So, here's what I want you to see. When you do momentum problems, you can start them at rest, boom, they go in opposite directions. One could be at rest, the other one moving, one stops, the other one keeps moving. You could have them both moving, okay? And then they move in opposite directions. You could have them where they hit, one's at rest, and then move off together. But here's how they all start. They all start with the sum of the momentum before equaling the sum of the momentums afterwards. And if you try and shortcut that process, this is where bad things happen. Okay, Vanessa, stop the camera. Back up front.